All right, thanks, Miles. We wanted to kind of switch tracks a little bit and look into broader support for machine learning, both from sort of design perspective for machine learning algorithms as well as utilizing machine learnings to derive insights from data on Spark. And there are like few things that I don't really have to talk too much about. We have been looking into this whole advent of big data that has been pushing quite a bit of boundaries in a lot of different areas that we have been witnessing now. So from Bosch's perspective, for instance, we have been looking into all the areas that span technologies like autonomous driving, for instance, looking into functionalities from highly automated driving, all the way to use cases within the domains such as the Internet of Things, connected components, connected assets, and whatnot. And when you start looking at kind of these scenarios and use cases, I think one of the core value generator here is not just the amount of data or how do we really manage this data around, but also to be able to look into how can we get insights off of this data. So most of these kind of value that comes out of this data is looking into ways to build machine learning algorithms, looking into ways to build, let's say, predictive analytics algorithms that can yield actionable insights that allows us to kind of make utilizations of it. So one of kind of this big space that we really look in this broader big data scenario is how do we really acquire, manage, and organize all this data. And we have seen over past years efforts in the context of kind of in-database computing, everything around kind of distributed computing in the form of MapReduce framework, as well as kind of in-memory computing where we have seen quite a bit of growth in Spark. And we have seen over the last few years, Spark is quickly becoming kind of a de facto standard for doing a lot of machine learning and data discovery within these large-scale systems. Now, in most cases, when we are talking about data discovery or doing machine learning in any of these scenarios, we are predominantly talking about optimization, right? So a lot of these machine learning problems at the end of the day are at the very core optimization problems. And in like more simpler cases, you would want to look into kind of the convex formulations of this. But in more real world cases, we would want to relax these assumptions and look into kind of more kind of ill-conditioned problems or essentially more non-convex formulations of our objective functions. So if you look into kind of the machine learning support that is available on Spark right now, we have relatively kind of sparse support, right? I mean, we have predominantly kind of MLlib and ML packages that allows us to do machine learning on top of Spark. And if I kind of look into the kind of bare bone capabilities that come out of it is the underlying optimization frameworks that these different packages utilize. Two packages are predominantly being utilized, right? I mean, so we do either the stochastic gradient descent or we essentially do our LBFGS, the limited memory BFGS kind of optimization. And they both are quite effective in terms of how they scale, but they also pose some very unique challenges actually. So if we look at gradient descent kind of setups, there is a huge dependency when it comes to convergence in terms of step size as well as the conditionality of the problem, right? So the ill-conditioned problems become sort of an issue in that setup. And a similar kind of thing with LBFGS where when we want to adapt these kind of setups to non-differentiable functions, these are very non-trivial kind of way mechanisms to adapt objective functions within that particular space actually. And those are kind of these two underlying limitations or underlying challenges that allow us to, that kind of essentially motivated us to look into algorithms that can essentially take our problem, scale it out, but at the same time give us some guarantees in terms of robustness as well as convergence, right? And if you see over the last few years, we have started looking into developments in this whole ADMM paradigm of optimization, where the broader idea is that in its very natural native form, it allows us to kind of take a large problem and break it up into smaller sub-problems, like simpler sub-problems that we can essentially optimize piecewise. And at the same time, it allows us to kind of derive some convergence guarantees as well as, we get sort of robustness around how quickly we want to get this optimization done. So essentially around the step size. And at the same time, it also gives us some robustness to the conditionality of the problem. And what we have been looking into is how can we take this setup and make utilization of this to address some of the challenges that we have seen in the classic optimization kind of setups that come with the current packages or current offerings within the Spark setup. So if I were to look from machine learning perspective, right, I mean, it's not just the fact that ADMM provides us like this generic formulation, but it's very amenable to Spark, as well as it provides this formulation that allows us to kind of provide a wide range of coverage to different machine learning algorithms, as well as you get more resources beyond sort of just MLlib or ML when it comes to kind of Python community utilizing Spark. So I mean, we have Python APIs that can be exposed, and at the same time it addresses some of this suboptimality that we discussed around SGD and LBFGS optimization formulations. So one thing that we wanted to do is essentially look into not just the coverage of all these different machine learning algorithms as well as kind of the accuracy and convergence guarantees, but we also want these kind of capabilities to be able to be utilized by a whole array of different practitioners. So everything from end users who are just going to utilize the capabilities via API calls directly, all the way to sort of designers who can essentially mix and match different optimization, different loss functions. So essentially create your own kind of pipeline in terms of different components of a machine learning algorithms, both in terms of loss as well as kind of regularization, as well as look, give support to developers who can contribute, who can, put in or add sort of new functionalities and new capabilities within this framework. And that was the whole idea of releasing this ADMML package, the acronym essentially standing for ADM-based machine learning package. And we have just released it publicly, last night. And we'll give some more details in terms of how it leverages the classical kind of machine learning optimization framework and how can we really extend it out to a whole kind of different variety of machine learning algorithms. So that's sort of our main goal here, and I'll kind of pass it on to Sauptik now to give you more details on kind of a deep dive on the package itself.
All right. Thank you, Mohak. So let's reiterate on what Mohak just recently said. So one of the first offerings that we provide through this ADMML package is like now we are solving a more generic machine learning problem, and we are solving it through ADMM. So the acronym being alternating direction method of multipliers, and through that we can provide robust guarantees and on the convergence of your algorithms, right? And in addition to that, what we provide to the community is like the entire package, the entire spectrum of the package is built in Python. So what it provides is like now you have accessibility to the entire machine learning algorithm, not just for the machine learning algorithms, which most of the current Spark-based ML tools provide. In addition to that, you have access as designers. That means you can select your loss as well as regularizer functions, and also like you have access to the ADMM engine, that is the optimization that you can do. So none of the existing machine learning tools available in Spark provide this at this point of time. So having said that, let's move on first to the generic machine learning formulation. As again, like for a typical machine learning problem, we are given with the training data where x belong to some d-dimensional space, and the task is estimating the y value, which could be in a real space or in a plus minus space. For real valued function estimation, it could be a real space. For binary classification, it could be a +1 or a -1. So the typical machine learning problems that we try to solve is minimizing a functional which consists of a loss as well as a regularizer, right? And the mixture of these different loss and regularizer results to different machine learning algorithms. So through this ADMML tool, we are solving a lot of machine learning algorithms. So we support the regularizers such as elastic NAT. Note that the elastic NAT formulation that we have currently, it's more generic in nature, in the sense that this elastic NAT formulation can also take care of regularization in the bias space as well. So the current existing algorithms, the current existing papers do not provide that, and this has been addressed in our paper in IEEE Big Data. In addition to that, we also provide a regularizer for the grouped regularizer, and the loss functions, which covers a lot of algorithms, are in terms of for classification, we have logistic regression, LS-SVM, squared hinge SVM. For regression problems, we have least squares, Huber, and pseudo Huber. So the main idea, what we do is like we solve a generic machine learning problem and we use ADMM to solve that. So to this end, I'm going to discuss how an ADMM algorithm works. Just to give you a brief idea how it works, it's pretty well known to the ADMM community, but to highlight why this is very amenable for the Spark distributed framework, what an ADMM algorithm does is like given a functional, which is a loss function and a regularizer, it tries to decompose this functional into smaller subproblems. So what it does is like it creates to a dummy variable, in this case a z, and it decomposes this function as a functional of w and a functional of z, right? And it decomposes this loss function and this regularizer. And to this end, it creates an augmented Lagrangian, but the main idea here is like it solves two smaller subproblems. In this case, it will first solve the subproblems for W update, which is an L2 regularized with the loss function. Then it will alternate into the direction of the Z update, which would also be the regularizer, L2 regularizer and the regularizer function. And finally, to have a consensus on the W and Z, it will have a U update. The main idea here is like what it does, it decomposes this larger problem into smaller subproblems, and which can be easily solved in a distributed fashion. Note that for most big data problems, the data actually comes through in the W update, where you have the loss function. And through ADMM, what only constraints is solving this W update, right? And note that this W update consists of the loss function and an L2 regularizer. So this L2 regularizer is a really amenable thing that we can distribute in the Spark framework, because this L2 regularizer has been well studied in the community and it can be easily distributed through a QP solver. And that's what we do through this ADMM algorithm. So to give you a brief idea about this, let's take a simple example of linear regression with probably elastic net regularizer. So as again, here we are given with the training data x and y, where y belongs to the real valued function, the real value space. We try to solve a problem as shown in this optimization. So the ADMM updates would look something like that. So let's not go into the details of the math, but what the main idea is like the data actually comes through this W update, and look at what this W update decomposes to. So in this case, the W update is majorly a matrix inversion and a matrix multiplication operation. Here it's P inverse and Q. So computing this P, you can easily do it in a distributed fashion. The way to do that is note that the only thing here is a summation over all the samples, and this can be easily done through a MapReduce update, and also the Q can be easily computed through a MapReduce update. So what we are effectively doing is like we are actually making a bigger subproblem. We are solving it into a smaller through smaller subproblems, which is an L2 regularizer, and it can easily be decomposed. It can easily be distributed for MapReduce updates. So that's the main idea of ADMM. In fact, we have shown a very simple example here for a linear regression. You can do that for multiple other loss functions, which we have already shown here. So the advantage through this is like this ADMM algorithm, there is a huge amount of research going on ADMM, and there is a definite need for the Spark community to address this, right? So through ADMM, you can actually show that your algorithms will definitely converge. Note that the current MLlib library, which provides an SGD-based update, you cannot show that. And also for LBFJs, the recent ML libraries, which is a very recent ML base, it does provide LBFJs updates, which has better convergence criteria, but for an SGD-based updates, it does not converge always. So through ADMM, you can guarantee this convergence. Again, what we have implemented in this ADMML tool is the most vanilla version of the ADMM available. There is a lot of research going on, and you can actually say that the convergence rate is really fast as compared to other this ADMM update as well. So having said that, the other thing that we provide through this tool is the accessibility of for different users. So now note that this entire tool has been built in Python. So this opens up the gap. It closes the gap between the Python community for optimization as well. Note that most of the machine learning libraries available for Spark, the optimization engine is majorly developed in some other language. So through this, it opens up research for optimization for Spark-based communities as well. In addition to that, it opens up access for the end users who can actually use the ADMM libraries, which is the least squares, all the different machine learning algorithms. It opens up avenues for the designers who can select the different loss and regularizer function to their own end. And finally, to the developers who can develop these optimization algorithms. So this is a unique gap. It covers up this gap between the researchers in the Python community and the Spark-based community, which was definitely necessary for ADMM research. Again, one of the limitations that we see here is like, note that this entire package is built on Python. So there are some speed restrictions when you build an entire package on Python as opposed to a Java or a Scala-based approach. So to this end, we wanted to find out what is the speed deficit that we see in this case. So this is an experiment that we perform. This is a synthetic experiment. As again, for our configuration, we had 6-node Hadoop cluster, for which we had 12 cores per node. We had a RAM of 64 GB and a hard disk of 2 terabytes. The Spark configuration was totally massaged based on the Cloudera blog, which is well known in the community. So the data we generated is a synthetic data, which is uniform data in a range of -1 and +1 in a dimension of 20 dimension. The Y is generated as shown here. And here we have an additive Gaussian noise. So for this, we generated two different kinds of data. One is a small data and a big data. For the small data, we have 1e⁻⁷ number of samples, which is approximately 5 gigs in a CSV format. For the big data, is 1e⁸, which is around 50 gigs. We call it big data because it's bigger than the size of the executor memory. So this is the table of time comparisons that we see. So as you can see, like in the first column is the performance of MLlib SGD. The second one is MLlb FGS, and the third one is the ADMM that we use. So the main understanding from the big data is similar to small data, so I'll just explain what it says. So the results here are the time in seconds, the average time in seconds over 5 experiments, 5 runs of the problem, and within parentheses we have the standard deviations. So as you can see, like for MLlib SGD, note that for SGD, one of the bigger issues is like selection of the step size. That was that Mohak was just speaking. In that case, like selection of step size actually determines like how fast your algorithm is going to converge, and it's not a very simple problem, right? So what we have seen, like for this kind of problem, it was really hard to get it converged, and the time taken to converge was around 1500 seconds for SGD-based update. For the LBFGS, the current problem that we are trying to solve is an QP problem because it's just a linear regression. It's a least square. So for an LBFGS, ideally it should just take one iteration, and that's what we see here. So LBFGS did convert in one iteration. For ADMM, it took 7 iterations here. But the main idea that I want to capture here is ADMM does provide competitive speed. Note that we are not comparing apples to apples here. We are comparing a Python-based package to a Spark-based, to a Scala-based package, but still ADMM do provide competitive speed in this case. In addition to that, as I have already mentioned, the ADMM tool that we have developed here, this is the most simplest ADMM tool. It's the simplest vanilla-style ADMM here. So there are a lot of new research going on in ADMM which provides much faster convergence. So in this case, we use the simple one, but however, if you use new research which was provided by Goldstein, in that case, the number of iterations took to converge was around 5, and that would speed up your convergence to around 485 seconds. Right. Again, like there are new research going on, there is an over-relaxed state which would actually let ADMM converge in just one iteration. Finally, one more point that I want to highlight here is like for MLlib, what it does internally is like given your data, it internally normalizes your data to a range of 0 to 1 for both X as well as Y values as well. So what it does, it like for cases where your data is not normalized or you need a different kind of scaling, in that case, like it may lead to suboptimal solutions. For example, for our experiments, what we found was like for the data, like with the optimal solution obtained from MLlib, the function value was around 15.07. However, the optimal value should have been around 12.34, which we obtained through ADMML. So what we claim here is like what you see is what you get, right? Whatever optimization you want to solve, you will actually get that optimal functional value through ADMML. So it's much robust for convergence in that case. So having said that, I would like to conclude this talk, but the main idea that I want to capture here is like what we provide through this ADMML tool is like this, we try to solve a generic machine learning problem. Note that we currently provide this tool with a number of machine learning algorithms, but it can easily be extended. Like that's a very generic machine learning problem. It can easily be extended to more machine learning algorithms, and that's something which is ongoing in our research. In addition to that, through ADMM, you can claim robust guarantees, or you can provide guarantees for convergence. And thirdly, the entire package is built on Python, so it provides accessibility for users in the Python community. So this is very useful for researchers and the Spark community to gel together. Having said that, as Mohak just mentioned, we just open sourced our code. It was just open sourced yesterday. So please feel free to use this code, and if you have any questions, feel free to send us emails and ask questions about it. So the current set of algorithms that we have in this code base is for classification for both elastic as well as grouped. We have logistic regression, we have LS-SVM, L2-SVM. For regression, we have D-squares, which would cover ridge regression, lasso, elastic net, group lasso, and so on, as well as Huber, as well as pseudo-Huber laws. In the future roadmap, we do have this, again, like this is the most vanilla version of ADMM that we have here. There are new research going on. The first topic that we are handling right now is selection of your step size. That actually reduces the number of convergence steps to half in some of the experiments. So we are working on that, and it would be available in the next cycle. For another thing that we are also working on is on the consensus ADMM. The version of ADMM, again, which I have shown is not the consensus one. There is another way where you can distribute the ADMM even more, and through that you can actually handle much more robust loss functions, the robust estimators, which are discontinuous in nature. And finally, we have already published some of our work on multi-class algorithms, like multinomial logistic regression and Kramer and Singer SVM in the Baylearn. So we are going to make that open source soon, and that's something which is in our roadmap as well. So with this, I'd like to conclude this talk. The contributors to this are already mentioned there, and I'd also like if you use this, please do cite our work in IEEE Big Data, and I'd also highly appreciate if you start using this and let us know how you like working with this tool. Thank you for your time, and thanks for everything.
Awesome. Thank you, guys. If you have any questions, please come up to one of these two standing mics and ask away.
So really good talk. I appreciate it. I'm not that familiar with ADMM. Is there, within the framework, is it possible at all to handle constraints, at least for some of the forms of the underlying, the underlying machine learning problem? Would it be possible to handle linear constraints, for example?
That's a very beautiful question. The question here is, like, as you can see right now, we are not using any constraints in the optimization formulation. So the question is, can we handle more constraints in the algorithm in itself? So the way to do that would be, it is possible firstly, and the way to do that would be like, again, like the constraints would be solved in a single, so you will have, the way ADMM solves is like it solves smaller subproblems, right? So when you solve those subproblems, you'll have to take this constraint into consideration through those subproblems, right? So another way would be like you can show an equivalence of those constraints with the regularizer itself or through the augmented penalty as well. And that would be one other way to handle those constraints. But typically, the main idea here is like solving the smaller subproblems. So ideally, the way it's done is like, means there are other works as well. What it does is like it clubs the constraints with some of those subproblems and just solve those subproblems in those constraints. Yeah. Thank you.
Awesome. If there are no more questions, let's give our speakers a round of applause. Thank you.
Thank you.